Hello, in this video we're going to go over final exam from fall of 2023 for multivariable calculus. Find the equation of the plane containing these 3 points. Your final answer should be in the form ax plus by plus cz equals d. Okay, so we have 3 points. We are given these 3 points, 2, 3, 2, 1, -1, -3, and 1, 0, -1. And we want to find the equation of the plane containing these 3 points. So in order to find a plane, we need a point and we need a normal vector. So we'll go ahead and evaluate a normal vector by finding AB cross AC. So how do we find AB cross AC? We will do a determinant. So AB is B minus A, so that's -1. -1 minus 3, that's -4. -3 minus 2, that's -5. AC would be 1 minus 2, that's -1, 0 minus 3, and -1 minus 2, that's -3. Okay, so let's go ahead and evaluate this normal vector. So we would get 12 plus 15 I minus, eliminated in the second column, we get 3 or this would be minus, in fact. So it's 12 minus minus minus. There are 3 negative signs, so minus 15. Eliminating the second column, we get 3 minus 5j. And then plus, eliminating the last column, we get 3 minus 4k. So simplifying that, we get minus 3i plus 2j minus k. So what is the plane? The plane would be -3 times, I'm going to use C as the point, x minus 1 plus 2 times y minus 0 minus 1 times z minus minus 1 equals 0. So let's distribute that. We get -3x plus 3 plus 2y minus z minus 1 equals 0. And following the instructions that they gave us, we will get -3x plus 2y minus z equals -2. So this is going to be the plane. Does the line with the parameterization this intersect the plane with equation that? So we have a plane and we have a line and we want to see if they intersect. How do we find the fact that these two intersect or not? There are two ways of doing that. Either we look at the normal vector and we check whether the normal vector is perpendicular to the direction vector of a line, or we solve a system of equations. Solving the system of equation would be better in this case because they're asking us to find the intersection point as well. So what we know is this. We know x equals t, y equals 4, and z equals 2t. And these are obtained from these 3 coordinates. And we also know that the plane is 2x minus 5y plus z equals -8. So we'll take that point and we plug it into the plane. So we will get 2t minus 20 plus 2t equals -8. So this gives us 4t equals 12. So that tells us that t equals 3. So the point of intersection is 3, 4, and 6. And we can plug in 3, 4, 6 into the equation. We get 6 minus 20 plus 6, which is in fact -8. Okay, so the next problem. Find the cosine of the angle between these two vectors. So cosine of the angle is going to be the dot product of the two vectors divided by product of the magnitudes, because the dot product is evaluated by multiplying the magnitudes and multiplying by the cosine. The dot product would be 1 the coefficients of I are 1 plus 2 plus 0, divided that by the product of the magnitudes, root 1 plus 4 plus 1, and then root 1 plus 1. So this would be 3 over root 6 times 2, that is 12. So this is going to be 1/2. So the answer is, or root 3 over 2. So the answer is root 3 over 2. Okay, so let's move on to the next problem. So they gave us these two parallel lines and they're asking us to find the distance between them. So how do we find the distance between two parallel lines? You take one point and then you find the distance using the distance formula. So if a point on the line is P0 and if a point outside of the line is P, then the way we find, and if this one is the direction vector, the distance, the formula for distance is going to be, so we'll have to take P0 and then cross that with V, and then we divide by the magnitude of V. So we'll have to find a P on one plane, on one line, P0 on the other line, and a direction vector. So what is P in this case? Well, we can take this one to be R1, or let's call that L1 maybe, because that's the parameterization, and this one L2. So what is a point on R1? You can set t equals 0. We get 1, negative 1, 2. That's a point on this one. What is a point on the other one? Plug in t equals 0. We get 0, 2, 3. So then we have to use that formula. And what is the direction vector? Direction vector is the coefficient of t. Coefficients of t are 2, negative 1, negative 2. And of course, it's the same for both of them because these are parallel lines. So we'll have to find the cross product of P0 and V. So this would be, again, ijk. P0 is P minus P0, so that's 1 minus 3, negative 1, 2, negative 1, negative 2. So this would be, we'll find the cross product of these two by eliminating the first column and first row. We get 6 minus 1i minus 2 plus 2j plus negative 1 plus 6k. So this is the cross product. Let's simplify this. This is 5i. The j component is 0 plus 5k. So the distance is going to be magnitude of this, root 25 plus 25, divided by magnitude of v, which is root 4 plus 1 plus 4. So this is root 50 divided by 3, which we don't have to simplify, but this is our final answer. Suppose the acceleration of an object at time t is given by this. Assume that the object has initial velocity v of 0 equals k and initial position r of 0 equals I. Find the position r of t of the object. So in order to find the position, we'll have to take the integral of velocity. In order to find velocity, we'll have to find the integral of acceleration. So we take the integral of that. This would be negative sine 2t over 2i minus, or rather plus, cosine of 2tj plus c. Now they told us that when we plug in 0, velocity is k. So at t equals 0, we get k equals sine of 0 is 0, cosine of 0 is 1, so j plus c. So this tells us that c is equal to k minus j. So this tells us v of t is equal to negative sine of 2t over 2i plus cosine of 2tj plus k minus j. We'll integrate this one to get the position. So r of t is going to be, so integral of negative sine becomes cosine. but there's a 2, so we have to divide by 2. So we get over 4I plus sine of 2t over 2j plus tk minus tj, and of course again plus a constant vector. Now they also told us that r of 0 is 1 is I. So at t equals 0, so what are we going to get? We get I equals, when we plug in t equals 0, we get 1/4 I. Sine of 0 is 0, t is 0, t is 0, so we get plus c. So that means c is 3/4 I. And the question was asking you to find position. So all we got to do is to plug in 3/4 I into c. So we get cosine of 2t, all of that over 4 I plus sine of 2t over 2j plus tk minus tj plus 3/4 I. So this is our answer. Okay, so number 4. Consider the parameterized curve this. Find the tangent vector t of t. So what is the tangent vector? You have to find the derivative of r. So r prime is going to be 2ti plus 2j plus t squared k. And then we'll have to divide by its magnitude. So t of t, let's find the magnitude of that first. So magnitude of r prime is going to be square root of 4t squared plus 4 plus t to the power of 4th. And let's simplify that. This is a perfect square, so this would be t squared plus 2. So what does that mean? It means the tangent vector is going to be 2t over t squared plus 2. We'll have to take the r prime and divide by its magnitude. I plus 2 over t squared plus 2 j plus t squared over t squared plus 2 k. So this is our tangent, and then how do we find the normal? To find normal, we have to take the derivative of unit tangent and divide by its magnitude. So let's do that. So we take the derivative of this. This would get a little bit messy. So derivative of numerator is 2 times denominator minus derivative of denominator 2t times the numerator divided by denominator squared I plus derivative of numerator times denominator, that's just 0, minus derivative of denominator times numerator times denominator squared j plus something similar again, derivative of numerator, which is 2t times denominator, minus derivative of denominator times numerator, all of that k. So let's simplify and then divide by its magnitude. So this is t squared plus 2 squared. We get 2t squared plus 4 minus 4t squared I minus 4t over t squared plus 2 squared j plus, so we get 2t cubed minus 2t cubed, so those two cancel. We get 4t over t squared plus 2 squared k. Okay, so let's simplify this and let's find its magnitude. So I'm going to rewrite that as minus 2t squared. And then we're going to take the magnitude. So t prime would be, so taking the magnitude, we get t squared plus 2 to the power of 4 at the bottom. And then squaring those, we get 16 plus 4 t to the 4th minus 16t squared plus 16t squared plus 16t squared. So 16t squared cancels, these two cancel, and we get 2t squared plus 4t plus 4 all of that squared divided by t squared plus 2 to the power of 4th, square root of that. Once we take the square root, we get 2t squared plus 4 over t squared plus 2 squared. Factoring it 2, we get t squared plus 2 over t squared plus 2 squared, which is 2 over t squared plus 2. And in order to find the normal vector, we'll have to take t prime and divide by the magnitude of t prime. Now, t prime already had a t squared plus 2 at the bottom. So if we look at t prime, we could get rid of one of the t squared plus 2's at the bottom and get rid of the 2. So we get 2 minus t squared over t squared plus 2i. I divided the numerator by 2 and I divided the denominator by t squared plus 2 minus 2t over t squared plus 2j, and finally plus 2t over t squared plus 2k. Right, but do not evaluate the integral that gives the arc length of the curve. So the arc length is going to be integral from 1 to 2. They gave us the limits of magnitude of r prime dt. So this is integral from 1 to 2. Magnitude of r prime is something we found earlier. We found it as a t squared plus 2. So t squared plus 2 dt. And that is the answer. Okay, so next problem. Define f of x, and this is supposed to be f of x y, as that. Find the directional derivative of f at this point in that direction. So because the direction is given as a non-unit vector, we'll have to change it to a unit vector. So unit vector is going to be 2i minus j divided by square root of 4 plus 1, which is the magnitude of this vector. So this is 2 over root 5i minus 1 over root 5j. So this is the direction. Now, in order to find the directional derivative, we have to find the gradient, and then we have to find the dot product of that gradient at the given point by the unit vector. So gradient would be y squared minus 3x squared y, 2xy minus x cubed. Let's evaluate the gradient at -1, 2. If we plug in -1, 2, we get 4 minus 3 times -1 squared times 2, 2 times -1 times 2 minus -1 cubed, which is 4 minus 6. 2 times -1 times 2, that's -4, and then plus 1. So this is -2, -3. So this is the gradient. Now the directional derivative is going to be -2, -3, dotted with the vector that we found, which was 2 over root 5 and 1 over, so 2 over root 5 and -1 over root 5, I believe. Let's go back, yeah. So we find the dot product of these two. This gives us -4 over root 5 plus 3 over root 5. So that is -1 over root 5. So that is the directional derivative. Find the value of the largest possible directional derivative. So the largest possible value directional derivative is the gradient, is the magnitude of gradient, which is exactly, we found the gradient, so it's exactly root 4 plus 9, so root 13. And this is the point that they gave us, -1, 2. So we already had done the calculation. Okay, so find the equation of the tangent plane to this graph at -1, 2, -2. Okay, so first let's write down the surface. It is z equals, so going back and looking at the equation, it was xy squared minus x cubed y. So this is the surface. And if we plug in -1 for x and 2 for y, we would have to get -2. And we could see that it's -4 plus 2, which is in fact -2. So we want to find the equation of the tangent plane to the surface at that point. So first we'll have to write it down as a level surface. So this is z minus xy squared plus x cubed y equals 0. So normal vector would be the gradient. So normal vector is going to be gradient of that, which is minus y squared plus 3x squared y minus 2xy plus x cubed and 1. So this is the normal vector. Now evaluated at given point at -1 to -2, that would give us the normal vector. So let's plug it in. And when we plug it in, we get -2 squared, that's -4, plus 3 times -1 squared times 2, comma, -2 times -1 times 2 plus -1 cubed and 1. So this is a normal vector. Let's simplify this. We get -4 plus 6, 4 minus 1, 1. This would be 2, 3, 1. This is a normal vector. So tangent plane is going to be 2, 3, 1. Those are the coordinates of the normal vector. And then the given point was -1 to -2. So -1 to -2. So this is the equation of the tangent plane. Okay, so next one. Let f of xy be this and r be the disk, x squared plus y squared less than or equal to 4. Find the absolute minimum and absolute maximum value of f over this region. Okay, so in order to find absolute minimum and absolute maximum values, we'll have to first find the critical points inside the region, and then we'll have to look at use the Lagrange multipliers theorem to find the maximum minimum on the boundary. So first, look at the critical points inside the disk. So that's the first thing we are going to do. And this is a disk of radius 2. So we have to take the partials and set them equal to 0. So 8x minus 4, that would have to be 0, and 4y would have to be 0. So this tells us x is 1/2 and y is 0, which is clearly inside the disk. Now let's evaluate, so 1/2, 0 is right here. Let's evaluate f of 1/2, 0. That's a potential minimum or maximum value of the function. So when you plug it in, you get 4 times 1/2 squared minus 4 times 1/2, and then 0, and then 3. So this would be 1 minus 2 plus 3, and that is 2. So this is a potential maximum minimum value. Now we will use Lagrange multipliers theorem. Okay, so what is the given function? The given function is f of xy equals 4x squared minus 4x plus 2y squared equals 3, subject to the boundary of that disk, which is x squared. I'm going to call that g of xy, x squared plus y squared equals 4. So we are trying to find maximum and minimum value of this function subject to the fact that x squared plus y squared equals 4. Now we can simplify this f of xy by substituting x squared plus y squared equals 4 into this one. This would reduce our computation. If you don't do this one, it's still going to work, but it's going to be a bit messy. So I'm going to take the x squared plus y squared and plug it in here. So I would get 2x squared minus 4x plus 2 times x squared plus y squared plus 3. So if I plug it in, I would get 2x squared minus 4x. This is 4. 2 times 4 is 8 plus 8, 11. So the system that we get is fx, which is 4x minus 4, equals lambda times gx. Fy, which is just 0, equals lambda times gy. Okay, so clearly the second equation is better to use. So lambda is 0 or y is 0. Let's try both of them. If lambda is 0, then we would get x equals 1 because the first equation gives us x equals 1. And since x equals 1, we have 1 squared plus y squared equals 4. So we get y equals plus or minus root 3. So we get 2 points from here. If y equals 0, then we have x squared plus 0 squared equals 4. So x is plus or minus 2. So now we have to check these points. So the points are 1, root 3. Okay, let's try that plus or minus root 3. But we know that the function has been simplified to this one, so I can plug it into here. So this is 2 times 1 squared minus 4 times 1 plus 11. So this would be 2 minus 4 plus 11, which is 9. So that's a potential maximum minimum. F of plus minus 2, 0 is going to be, those two would have to be done separately. So that's 2, going back and looking at the function, it's 2x squared, 2 times 2 squared, minus 4 times x plus 11, I believe. 4 times x, which is 2. So this would be 8 minus 8 plus 11. So this is one possibility again. And if of negative 2, 0 would give us 2 times negative 2 squared minus 4 times negative 2 plus 11. So 2 times negative 2 squared, that's 8 plus 8 plus 11. That's 16, that's 27. So what is the minimum and what is the maximum? Well, the maximum is, we have to compare these values, 9, 11, 27, and what we got earlier, which was 2. So the maximum is 27, and the minimum is 2. Okay, let's move on to the next problem. Rewrite the following integral as an iterated integral in cylindrical coordinates and then evaluate. Okay, so let's look at the bounds and draw the region corresponding to these bounds and then turn it into cylindrical and evaluate. So the first thing that they gave us are the limits of z. So z is between 2 and 4 minus x squared minus y squared. So z equals 2 is right here. It's a plane. Z equals 4 minus x squared minus y squared is a paraboloid that is opening down. So we get a surface like this, and it's bounded below by z equals 2. So this is our surface. Now, if you look at the limits of y is between 0 and root 1 minus x squared. So what's the intersection of these two surfaces? So if you look at these two surfaces, we have the intersection is 4 minus x squared minus y squared equals 2. So this gives us x squared minus 1 plus y squared equals 2. So the bounds for x and y are actually not this disk. They are a smaller disk. So this is going to be the bound on the xy plane. So it's like that. And then of course x goes from -1 to 1. But they told us that y is only the positive portion. So it's only a semicircle. So let's actually draw this one on the xy plane. That would be a little bit easier to follow. Let's draw the region. Y is between 0 and root 1 minus x squared, and x is between -1 and 1. On the xy plane, this is a semicircle of radius 1, So only this portion. So the projection onto the xy plane is something of radius 1 rather than something of radius root 2, a disk of radius root 2. So it is in fact going to be something like this. This is our base. So the base is like that. This is our base. So the region is above this base and below the paraboloid. So it's a region like this. It's a solid like this. Okay, so we can turn that into a cylindrical coordinate by writing it down as r dz dr d theta. So dz, what are the limits of z? And the integrand is y, so I can write it down as r sine of theta. What are the limits of z? Z goes from bottom of 0 to the top of 4 minus x squared minus 2. Sorry, bottom of 2 to the top of 4 minus x squared minus y squared. So it would be 2 to 4 minus r squared. Limits of r are from 0 to 1, as we see from the projection onto the xy plane. This is how we find the limits of r. And limits of theta are going from 0 to pi. So let's evaluate this. 0 to pi, 0 to 1. Okay, so this one is r squared sine theta. When you do dz, you just get z r squared sine theta, and then z goes from 2 to 4 minus r squared, dr d theta. Next, we're going to go ahead and evaluate this one. So we get integral from 0 to pi, integral from 0 to 1. When you plug in z equals 4 minus r squared, you get 4 r squared sine squared theta minus r to the 4th sine of theta. So that's when you plug in 4 minus r squared, and then minus 2r squared sine of theta dr d theta. Now these two combine to 2r squared, so these two become 2r squared sine of theta. So when we integrate 2r squared, we get 2r cubed over 3 sine theta minus r to the 5th over 5 sine of theta. And then the limits of r are from 0 to 1. Okay, and this is a relatively easy integral to evaluate. So integral from 0 to pi. When you plug in 1, we get 2/3 sine of theta minus 1/5 sine of theta d theta. Okay, so what is that? This is 0 to pi. Taking the common denominator, we get 15. We get 10 minus 3. That's 7 sine of theta d theta. So this is negative 7 over 15 cosine of theta, theta from 0 to pi. When we plug in pi, we get 7 over 15. And when we plug in 0, we get negative 7 over 15, which is 14 over 15. Okay, so next problem. Using spherical coordinates, write the iterated integral that computes the volume of the solid region inside the sphere centered at the origin with radius 3 and below this cone. So let's draw the region first. So we have inside the sphere and below the cone. So we are given this cone and we are trying to find the volume of this region. This is the region we're trying to find its volume. And of course, the axes are as usual. Okay, and they instructed us to use the spherical coordinates. So we'll have to first figure out the limits of rho, limits of phi, and limits of theta, and then put it into an integral. So limits of rho are from 0 to whatever the radius is that they told us that the radius is 3. So radius is 3. Rho goes from 0 to 3. Phi goes from the cone to the bottom. So let's first figure out what the cone is. Cone is z equals root x squared plus y squared, which is r. Z is rho cosine of phi R is rho sine of phi. So that tells us tan of phi is equal to 1 and phi is equal to pi over 4. So the volume becomes triple integral of 1. So the integrand is 1. So now we'll have to put the Jacobian rho squared sine phi d rho d phi d theta. Limits of rho are from 0 to 3. Limits of phi are from pi over 4 to pi, and limits of theta are from 0 to 2 pi. So that's the volume. And they did not ask us to evaluate. In fact, they specifically asked us to not evaluate. Let sigma be part of the parabolic sheet 9 minus x squared. Y equals 9 minus x squared. In the first octant. So 9 minus x squared in the first octant will look like this. This is 9, and it's opening down towards the negative y-axis. So part of the parabolic sheet in the first octant below z equals 5, and z equals 5 is right here. So we have a situation like this. So this is our solid. Although they said it's a surface, so this is our surface. Consider the following surface integral. Parameterize the surface. To write this integral as an iterated double integral, do not evaluate. Okay, so how do we parameterize this surface? We can parameterize it using x and z. So r of x comma z would be x comma y, but y is given as 9 minus x squared comma z. Then we'll have to find r sub x, that is 1, negative 2x 0. R sub z, that is 0, 0, 1. Then find the cross product of these two, Rx cross Rz. Okay, so we eliminate the first column, we get negative 2x. Eliminate the second column, we get negative 1. And eliminate the last column, we get 0. Okay, so this would be our normal vector, but we'll have to find its magnitude because it's a surface integral of a scalar function. So this would be root 4x squared plus 1. They said parameterize the surface to write this integral as an iterated double integral, do not evaluate. So we'll set it up. Okay, so the integrand was yz. Y is 9 minus x squared. 9 minus x squared. Z is just z, and then we'll have to do dx dz. We'll have to multiply by the Jacobian. We found the Jacobian to be root 4x squared plus 1. And then we need the limits of x and z. So limits of x and z come from the xz plane. Limits of z are 0 to 5. This is the region on the xz plane. And we have to find this point right here. So for what value of x do we get 0 for y? That is x equals 3, because this is y equals 9 minus x squared. So for 3 we get 0. So limits of x are 0 to 3, and limits of z are from 0 to 5. And they did ask us to not evaluate. Let C be the clockwise oriented triangle with vertices these. So let's draw that. One of them is the origin, one of them is 4, 4, and one of them is 0, 2. So it is right here. So this is our triangle. So let's C be the clockwise oriented, so it means this way. This is our C, and we want to find this line integral. So what would be a good way of evaluating this line integral? The good way would be to use Green's theorem, because this is a closed curve. So we will use Green's theorem. So when we apply Green's theorem, we need to have the region. This region, I'll call that R. So the line integral of 5x dx plus x squared dy is going to be, since this is clockwise, I'll have to put a negative sign, and then derivative of this one with respect to x, which is 2x, derivative of the other one with respect to y, and then dA. Now we'll have to use, we have to put the limits of integration, and in fact we have to evaluate this one. So this is a vertically simple region. We need to find the two lines, bottom and top of this region. Bottom is just y equals x. This line is y equals x. The top line has a slope of 1/2, so this one is y equals 1/2 x, but the intercept is 2. So both of these 2 points, 4, 4, and 0, 2, satisfy that line. So it would go from, I'll do dy dx as a vertically simple region. Y goes from x to 1/2 x plus 2, and x goes from 0 to 4. And the rest is a very easy computation. So minus 0 to 4. Integral of 2x with respect to y is 2xy. Y from x to y equals 1/2 x plus 2 dx. This is equal to minus integral from 0 to 4. If you plug in 1/2 x plus 2, we get 2x times 1/2 x plus 2 minus 2x squared dx. Let's multiply, simplify, and then integrate. So we have a negative sign, which I'm going to make sure to keep. Multiplying this, we get x squared plus 4x minus 2x squared dx. This is going to be integral from 0 to 4, 4x minus x squared dx. And then we're going to evaluate the integral. So this would be 2x squared minus x cubed over 3. And then from x equals 0 to x equals 4. X equals 0 gives us 0. X equals 4 gives us 2 times 4 squared minus 4 cubed over 3. So that is minus 32 minus 64 over 3. So that would be our answer. Okay, last problem. Let D be the solid object above the xy plane and below this cone. So we'll draw the solid region. We have 4 minus root x squared minus y squared. Solid region above the xy plane and below this cone. So it's this region. Let sigma be the boundary of this solid oriented inward. So it's like this. Orientation is inward. Evaluate the following integral. Okay, so because it's a closed surface, we will use the divergence theorem. So we will use the divergence theorem. So we get triple integral over D, and because the orientation is inward, it would be minus, and then we'll have to take the divergence of this. What is the divergence? It's 2 plus 0 plus 7 dV, and this is negative 9 times volume of D, which is negative 9. Okay, so what is volume of D? This is a cone, so the volume is 1/3 times height. Height is 4 times pi, and then the radius squared, the area of the base. Well, the area of the base, the base is a disk, and the radius is 2 because it's, or the radius is in fact 4 because it's root x squared plus y squared equals 4. So the radius is 4, so pi radius squared. So again, it is minus 9 because of the constant that we took out. Volume, it's 1/3 times height times 1/3 because of the cone, and then the height times area of the base. And you could just leave it as that. They didn't ask us to simplify. Okay, last part of this problem and the exam. Let C be the curve parameterized by that. Evaluate this line integral. So now if you notice this line, this vector field is in fact conservative. So if you evaluate the curl of this one, you'll see partial of this one with respect to x and partial of this one with respect to y. Those are both 2x. So this is conservative. So let's find a potential function. So we will find a potential function. So we have f sub x equals 1 plus 2x y. F sub y equals x squared y. This gives us f equals x plus x squared y plus g of y. Take the partial with respect to y, we get x squared plus g prime y. Oh, this was x squared. G prime y equals x squared. So this tells us g prime of y equals 0. So g of y equals 0 is a possibility. So that means a potential function would be x plus x squared y. This is a potential function. Now that we have a potential function, we can plug in the endpoints. They told us the endpoints are 0 and 4. So the line integral is going to be f of, if you plug in 4, we get 8 for the first component. And the second component would be 8 minus sine of pi, which is 0. So that's also 8 minus f of, when you plug in 0, you get 0 squared, which is 0. 2 times 0 minus sine of 0, that's also 0, minus f of 0, 0. Okay, let's plug in 8 for the function. We get 8 plus 8 squared times 8 minus 0 squared times 0. And that is our answer. So 8 plus 8 cubed. So this is our answer. So I will see you in the next video.